let us continue our discussion on conservation of energy. So, in the last lecture we took an example in which a car was moving horizontally in a highway. Let us now discuss in this today about some particle or something that moves in the perfectly vertical direction. So, what will happen? Let us say I have some pointer in my hand. What will happen if I can throw it perfectly vertically upward? So, as you know from experience that let us say I throw it with some initial velocity v up in the upward direction. So, then is at this position t equal to 0 is kinetic energy is half mv square, and then we know that it will gradually reduce its speed, and after some time it will reach a position of 0 speed, and then it will start to fall, and then it will come back to my original position. Now, in this case what are the forces acting on this object? So, there are of course the gravity, the attraction due to the earth, and then there are the drag force due to air. Now, imagine that we are going to, suppose we ignore the drag on this particular object. So, this is makes reasonable sense if the speed of the object is very small. So, let us assume that there is only the gravity is the only force acting on this object. Then we know that as it goes up and stops and then falls, and when it comes back to its initial position, we are going to recover the same kinetic energy, which means that its speed at the initial, when it returns to the initial position, will be exactly same as the speed with which it started, only its direction will be now in the direction will be in the downward direction, the speed will be same. Now, that means that, so let us now ask that we learned from last class that the reason that the kinetic energy changes is because there is a force acting on the force by the gravity acting on this particle, and there is work done against those force, and that is why the kinetic energy changes. So, this was the work energy theorem. So, the kinetic energy converts to the work done against gravity, and now when it falls, this work is again gets converted into, because now the gravity is in the same direction as the speed, as the velocity. So, it again converts back to the kinetic energy, and when it comes back to the original position, we recovered, if we ignore friction completely, we recovered the original kinetic energy completely. Now, this is a case in which we can simplify the work energy theorem even further. So, remember the work energy theorem, the way we wrote down in the last class was the half m v naught square minus half m v square is the work done. So, the change in the kinetic energy is given by this particular extension, the work done on the particle. So, this is a 2-point equation. Now, there is this special case of conservative force. So, these are the force, this force, there are certain forces for which we can simplify this even further. So, these forces which are denoted as conservative forces, this has this property that the work done on a particle between two given points is independent of how the particle makes the journey. So, for example, if it goes from this position x naught to x, this journey does not depend on the path of for the conservative forces. Now, if this is true, now when can it be true? In 1D. So, in 1D the options are limited, because the path is a unique path. In 1D you can go from point 1 to point B, point 2 by a single unique path. Now, from our calculation before, we see that if the force is only position dependent, then for that force this statement must always be true, that it must be a conservative force. So, this comes from our derivation of this theorem, that if the way we derived to this f was m v dv dx, and then this work done was x naught times x, which is half m v square minus half m v naught square. So, if f is a function of x, then this integral will depend only on the end point. This is the essential mathematical point. Now, are there examples of such force? Well, of course, there is, like I can give two common examples. First is the weight of an object mg. So, this is a force that is constant, and remember that when I say force is a vector, so the force is a vector. So, if force is constant, it must be constant in both magnitude as well as direction, which is true for weight. And another common example is spring force. So, if we have this kind of force, or which are called conservative force, we can define a function called the potential energy function, and in this case we can simplify. So, this expression for work energy theorem, which is between 2 points, to a single point. For every single point we can define an invariant quantity, which is going to be the total energy of the system. So, let us try to understand this through an example. Let us try to work out through an example. So, suppose there are 2 point masses capital M and small m. So, imagine that the capital M is sitting at the origin, and r represents the distance between of the small m, the mass point small m from the capital M, the distance separation between the two objects. So, they are separated by a distance r. What is the potential energy of the system at separation r? So, what do I mean by that? So, let us start with this, that we are going to calculate this work done for, let us say, if we go from some point r naught to some point f, then what is the work done? So, the separation changes from some distance r naught to some distance r. Let us, this is r, this is r naught. So, how much is the work done by the forces? And this is the force of, what is the force between these two objects? This is the gravity force, and which is given by the Newton's gravitational law. So, we are going to calculate this, and we know that if the separation is r, then the force between the two objects will be given by Newton's law of universal gravitation. And note that in this case, this is completely a function of only the position, or in this case the separation between the particles. And if we calculate this integral, we get so now if we combine it with the work energy theorem, so between these 2 points the kinetic energy also changes because of the work done by the force of gravity between them, and by work energy theorem. So, this must be equal to half m v square minus half. So, by work energy theorem they must be equal, and hence this must be equal to so if we rearrange term, so then we see that we can rearrange the term and for every position of the particle we can define a quantity which can be computed only by the information of that particular position. For example, at the position r, the speed is v and the separation is r, at the separation r. So, this left hand side, it depends only on this separation r, does not contain anything about the r naught, and similarly right hand side does not contain anything about r, only contain about the separation r naught. And traditionally this is written as a position function where Vr is given by, and this function which can be defined for any position, or in this case the separation between the distance between the two objects as the potential energy function. So, this is a function such that if we integrate, so then we can, using this definition, we can write this work done So, there is an integral, so such that the derivative, if we take the derivative of this function, we get the force or negative of the force. Which you can verify. So, this is the potential energy function, and using this concept of potential energy function, which is the integral related to the integral of the work done by the force, then at each point we can define a quantity. So, we see that this value of this quantity is same at point r as well as point r naught. So, this is an invariant which is called the total energy, and this is an example of an invariant. So, this is the answer. So, this potential energy is given by this particular expression, and using this particular expression we calculate an invariant quantity which is denoted as the total energy, the kinetic energy plus potential energy as the total energy of the system. And remember that when you apply the conservation of energy, the choice of system can be very tricky. So, you have to define very carefully which forces are there and what is your system and what is the force for which you are calculating the potential energy. So, let us try to clarify it further using another example. So, this time we are taking a spring. A point mass small m is connected to a spring with spring constant k. What is the potential energy of the system at this stretch of the spring, where is x? So, x equal to 0 denotes the unstretched spring. So, when the spring is at equilibrium, if we stretch it, then it will try to come back to equilibrium, and hence the mass m feels a force which is given by, we know, which is proportional to the stretch x, and it is and the proportionality constant is called the spring constant, and it is the minus sign denotes that it is the direction opposite in which it is opposite of x. The sign is opposite to the sign of x. Now, if we apply the work energy theorem, so let us say that we want to calculate the work done on the particle against the spring force, and then this work done is given by, which is so now if we equate this to the change in the kinetic energy, and then if we rearrange term, again we find that we can define a function for a single point. So, this is the kinetic energy, so we are just rearranging the term from one side to another side. So, the left hand side is a function of only the point x, and the right hand side is a function of only the position where the stretch is x naught, and this is the kinetic energy and this is the potential energy, and this is the total energy. Again, this total energy is an invariant which is the same for all these different points. So, again you see that if we try to analyze the motion of the spring directly using solving Newton's law, then we have to follow the position and velocity of the mass frame by frame at every instant, but the conservation of energy gives us a shortcut, so that we can take any two position of the spring equilibrium position, extreme length position, any position, and connect them by an equation, and this equation represents the physical fact that there is something called the total energy, which is invariant, which does not change as the spring changes its position. The mass changes, spring changes its stretching, or the mass changes position. So, now our next part is of today's discussion is going to be a little bit mathematical. So, we are trying to generalize the concept of work energy theorem and the concept of conservation energy to higher than one dimension. So, the maths is going to be a little bit more complicated. So, by higher I means 2D or 3D and so on. So, the issue is that suppose the same question we are asking, that we have this system and it has two position. The first position is r naught as some initial position, and the final position is r, and we going to ask how much, and there is a force acting on the particle or our object system, and the question is that what is the work done on the particle. Now, in 3D for example, or any or even 2D, the difference is now that earlier our expression of work was just F times displacement, but now there are many different ways. So, this is the key point, that when we go to 2D or 3D, there are many different ways to go from point 1 to point 2. So, the path is now no longer unique. So, in 1D there is only one way to go from point 1 to point 2 if you are moving along a line, but in 2D for example, on this plane there are infinite number of ways. In 3D there are also infinite number of ways, and more ways in 3D than in 2D to go from a point 1 to a point 2. In that case, what we have to keep in mind is, when you calculate the work done, that we need to know which path the particle followed. So, the work done in 3D or in any higher D, even in 2D, is in general path dependent. So, if we specify the path, then the total work. So, now we can generalize the expression for work. So, instead of one single piece of displacement along, let us say, x direction, now we have three independent piece. One corresponds to the x direction, second movement along y direction, and third movement along z direction. Why three independent piece? Because any displacement in 3D, so here we are taking the expression of example of 3D, we can always compose the displacement into three components, one along x direction, one along y direction, one along z directions, for x, y, z are mutually perpendicular axis. So, then our expression for work will consist of three pieces. The first piece is the moving along x, three one dimensional piece, and you have to sum over them. And from, so this is the one side of the equation, and we got this expression that F is mv dv dx in 1D. So, F times dx is equal to mv dv. So, this is true now for each of the separate x along this x, y, z separate directions separately. So, on the right hand side will be similarly composed of sum over three pieces, one for x direction, one for y direction, one for z direction. And hence, going from a point r naught to r is equivalent to the x naught coordinate x naught changing from x naught to x, y changing from y naught to y, and z changing from z naught to z. And then we can sort of have, so if we do the integral, then we get an expression for kinetic energy again. Now, this algebra becomes more elegant if we use our vector notation. So, in vector notation, so this work done, so the expression that we get for work, by looking, it is obvious that it can be expressed as a dot product between the two vector, the vector f with component fx and fy and fz, and a vector dr, which represents the displacement with component dx, dy and dz. So, then if we take dot product of these two vectors, you can easily verify that we get back this particular expression. So, then in this case the work done between 2 points. So, we have this work done. So, this is the work done on the particle, this is the kinetic energy of the particle. So, between 2 points we get this particular expression, that half m v square minus half m v naught square is equal to the work done on the particle, which is now a integral, a strange integral in 3D. So, this is called a path integral, so a line integral. So, we have to specify a particular route by which the particle goes from r naught to r, and then you can compute this quantity. And because in 3D or even in 2D there is no unique path. So, this the right hand side is in general depend on the route that the particle takes, and hence the kinetic energy change will also depend on the route that the particle changes. So, this is the generalization of work energy theorem in 3D, which works also in 2D. So, this is again the point is that again I emphasize the key issue. The key issue is that in higher dimension, higher than one dimension, the path is not unique. But we can still ask this question that in like in 1D we took two examples like the gravitational force and the spring force, for which this integral of work done was independent of the path followed, and it depends only on the end points. So, we could define a potential energy function, so that the integral, this particular integral, the value of this integral depended only on the end points, the x naught and x. Now, is it true in 3D or 2D also? So, the answer is yes. So, there is a so we can also have conservative force for which this property is true, that this journey going from point A to point B, so does not depend on the path that we follow. So, it will depend only on the end point of this path. So, there are certain special forces for which indeed it is true even in higher dimension. So, the question is that in higher dimension or any dimension, when is a force conservative? So, you are going to show this mathematics, this analysis using the, so you are going to sort of use it as kind of an exercise in vector analysis. So, the condition is that if there exists a function V r, which is a potential, which will anticipate to be the potential energy function, such that the work done depends only on the end points, then we will have a conservative force. So, this is the definition of the potential energy function in 3D. So, now the work done for a small displacement dr is given by this dot product between the force times displacement, both of which are vector, and the overall work done along a path from r naught to r is going to be the difference in the potential energy. So, there exists such function such that this work done will depends only on the endpoints and the values of the endpoints of the potential energy function at the endpoints. Then if we compare, we can say that this small change, this can only happen if this small work done, infinitesimal work done at certain points r prime between r naught and r, must be represents the small change in the potential energy. So, this is formally written as this particular equation. Now, since this is a vector, you cannot divide a scalar dV is the change in the some energy, a scalar which is a single number, you cannot divide both sides by a vector, that is not, do not divide. This is very important. Instead, we define a function, it is a new symbol which is inverted triangle with a vector. It is called a del operator or a vector operator. So, think of it as some kind of a rule with multiple components like a vector, which acts on a scalar and gives you a vector. So, what is this operator del? So, this is called del or nabla. So, let us understand this. So, I am going to take first the Cartesian components and in 3D. So, suppose in Cartesian components it is function v which you can define at each point in space. So, each point in space is denoted by 3 numbers, 3 coordinates of that position x, y, z. So, v is a function of the position of points in space. Then by calculus, elementary definition of calculus, a small change in the function v dv is given by the this right hand side expression, and if we compare these two expression, then we arrive at the a relation between the components of the force x, y and z component and the derivative of this potential. So, the x component of force is nothing but the negative of the partial derivative of v with respect to x, and so on for the other components. So, note that this is now a partial derivative, which means taking this derivative keeping y z equal to constant. This means that taking the derivative with respect to y keeping z and x equal to constant. This is the meaning of partial derivative. Since we have now many different multi-component function, multi-variable function, so we cannot use a total derivative, we have to use a partial derivative. And in this particular case, the displacement is given by this vector. This is the displacement vector. So, let us now take another example of expression for del. So, okay, so we have already discussed the expression for del in or this operate this. So, this del is called an operator, which means is a rule and it has multiple components. So, it has a components is a vector. Note that a vector operator, it does not have a direction, it just means it is a rule with multiple components. So, this one we say that, imagine that if we take this as if this is a rule. So, the rule is to take derivative. And this particular rule acts on the function v is equal to the grad v, and this is a, so the rule, so the resultant quantity is a vector, and this can now taken a dot product with the displacement, and that will produce this particular expression. So, that if we compare with the work done, then the force is given by grad v, where the components are worked out in 3D in the Cartesian here. So, now just to show it further, so we can also, we do not need to take Cartesian component, we can also take other coordinate systems. For example, in, let us for simplicity let us take a 2D coordinate system. So, in 2D we can take the Cartesian coordinate system, but we can also take what is called a polar coordinate system. So, this is the origin and you join some point P with the origin, then the position vector of this point. So, the distance is r, and the angle it makes with the positive of x axis is the orientation of this vector. Now, with this, and then you can imagine that the position is now given by two numbers r and theta. So, this potential energy function, which is again defined at each position of a point particle. So, it is a function of r and theta. Again the calculus shows that a elementary small infinitesimal change in v is given by this particular expression of the right hand side. So, if we look at the displacement of a particle, now the displacement is not simply dr plus d theta, but dr, which is a displacement component in the radial direction keeping theta constant, and this is a displacement in the tangential direction. So, if this is a delta theta, it is exaggerated, then this displacement is r times d theta. It is not only d theta, but r theta multiplied by r. So, then the displacement in if you keep r constant, this radius r constant and go in the tangent direction, then the displacement is r d theta times theta. So, then if we now write down the expression for the work, then as f dot dr, then we get so the f is we expect that it must have a component in the r direction and radial direction and a component in the tangential direction. So, this will be the two components of f, and then this f times displacement and fr radial component times the displacement in the radial direction, that is the dot product. And then by comparing this line with this line, we get an expression for the del operator. So, if we say that this force is minus gradient of v, then we can express it as r So, this will be the expression of the this operator del, which acts on the potential energy function to produce the force. So, now coming back to our question, that what is the condition that the force will be conservative in higher dimension, in higher than one dimension, or in fact this is also what we have discussed is going to be true for any dimension. So, this we are going to state without proof, because the proof is beyond the scope of this particular course, but I am certain you are going to learn about this in a mathematics course or on vector analysis or a electricity magnetism course. So, given a force Fr, so F is a vector, so it is denoted as a bolt, tie it, and R is also position, it is also a vector. So, necessary and sufficient condition for the potential function Vr to be path independent and well defined. So, that means that whether we can find a function potential energy function V such that we can express this F integral of work done as a kind of a proper as just by given by the endpoints. So, there is a well defined Vr function exists as a condition. The necessary and sufficient condition is that another operation curl of f. So, this is the symbol of curl of f. So, again the same operator del, and now this is a cross product. So, if you act, so there is a different rule, a different operator, different vector operator which acts on f for vector and produces another vector which is called curl of f. And the condition that for the existence of potential energy function is that this curl of f must be 0 everywhere. So, here I just mention for the sake of completeness how to write down this rule curl of f in Cartesian components in 3D, which is just given here. So, you can sort of work it out, but I am not going to say more about that. Instead, let us try to illustrate it through an example. So, there is a very important class of forces which are called central force. They are very important in 3 dimension. So, their property is that this is a force such that, so suppose this is a origin and this is a point P, this is origin, and the position of P with respect to this origin is r. So, then let us say something on P sits, let us say there is a point mass something like a sun which is sits at O, and let us P may be the position of earth. Then there is a force, the particle or the point mass at P is feeling a force, and this force is such that the magnitude of the force, which is the F without the vector sign, depends only on this distance r, and it has no tangential component. So, only component is radially. So, the F can be directed along OP either towards OP or away from the OP. In the case of gravitational force, so this attraction is attractive force. So, it is directed towards sun is attracting earth towards itself. If we have 2 point charges, one at O, one at P, with the same, let us say 2 electrons with the same charge, then this could be repulsive. The force on the electron at P will be by the electron at O will be repulsive. So, it is along r. So, this force is along r or along minus r. Then if this is the case, then so this force is a conservative example of a conservative force, which means for which there is a well defined function, potential energy function, which we know exists, because we know the gravitational force has a gravitational potential energy function and the Coulomb's force has a electrostatic potential function. So, here we just verify that if we have a force like this, then the curl of F will be 0. Now, we are going to use this expression here, this rule that is provided here to compute the curl of F, and it is sufficient to calculate only for x component. If it, I mean likewise you can show the other components will be similarly 0. So, only thing to note, so you have to calculate this quantity x, this is the so one component, this is the z component of the curl of F. So, the Fy, so in the Cartesian coordinate system, this is Fr, and this r hat is given by is a unit vector. This is a unit vector. So, this is the actual position vector divided by the magnitude, and this r, the position vector r, as you know in Cartesian is given by this particular expression. So, r hat is given by and then if I, so this is r hat x component. So, F times x by r x hat plus y by r y hat plus z by r z hat. So, if x is f x by r, if y is f y by r, and if z is f z by r. So, now plug in all these quantities and then you just calculate the derivatives. Only the one thing you have to remember, so there is this identity that you should use, that r is square root of x square plus y square plus z square. So, suppose if we have del r del x, which is given by, so if I apply chain rule, we get x square plus y square plus z square to the power half, so half into 2x, because del y del x is 0, del z del x is 0. So, these 2 gets cancelled with these 2, then this is r. So, this is x by r, which is written here, and similarly for the other components. Now, if you apply this rule and just plug in this chain rule, then you will see that everything will get cancelled and you will end up at 0. So, for a central force, the curl of F is 0 everywhere, and hence this force is as a conservative force. So, I am just to summarize what we discussed today. So, we discussed the conservation of energy, we discussed generalized the work energy theorem from 1D to 2D and 3D and higher dimension, and we discussed conditions under which in higher the main issue the main difficulty when you go from 1D to higher D is that the path that a particle can take to go from point 1 to point 2 is no longer unique. Under this situation, we can still define a conservative force, and we discussed what are the conditions for a conservative force to exist, and we say that if the force is conservative, then what is the relation between the potential energy function and the force, and what is the condition that, and we finally we discussed that if the curl of the force is 0 everywhere, then the force must be conservative. In the next class, we are going to discuss conservation of momentum and momentum balance principle. See you next time.